All right, welcome to hypothesis testing video number 5. As always, we are reminded by Google that I can broadcast for 8 hours, which sounds just like the worst idea ever. So let's get going with this broadcast. Let's just talk about what's going on with excuse me, with hypothesis testing at this point. And we've gone through the logic of hypothesis testing, and I hope you've figured out generally what the logic of the hypothesis testing process is. But now we have to talk about a very specific outcome of hypothesis testing that we talk about an awful lot in psychology, a p-value. There have been jokes made about the fact that it's the p-value that we're obsessed with in psychology, but well, make your own jokes. Anyway, the learning objectives today are to help you understand a little bit more about hypothesis testing by using metaphors and analogies, and specifically to understand p, the p-value. And we'll talk about what that is. There's no simple, small sentence that tells you what p means. P is the probability of a big conditional probability statement, which you're actually familiar with already. So we'll talk a little bit about that. Hypothesis tests are all about using data, and the data might have come from a world where the null hypothesis is true, and we just say, you know, if the null hypothesis is true, or if the null is true. We've been talking about this so much at this point in psychology and in science in general and statistics that we use a lot of shorthand notation to talk about this stuff. Or from a world where the alternative hypothesis is true, and we don't know where this data came from. And then we make a reasonable guess about the null hypothesis. If you recall, the null hypothesis is the only one that we directly test in traditional hypothesis testing, which is problematic, but it also has some advantages. So the decisions that we make, the guesses that we make are, do we reject the null hypothesis as a believable or plausible explanation for where this data, the results of this study might have come from? Like, is the null hypothesis being true? Is that the reason we got this data, or is it that it's false and that's the reason we got this data? We're going to make a guess, a reasonable guess, not a lame guess based on, you know, unknown factors, but a guess based specifically on the data and some probability theory. So do we reject it and therefore retain the alternative hypothesis, or do we do the opposite? Do we retain the null hypothesis and therefore for now reject the alternative hypothesis? So statisticians like to have a little bit more precision than just saying, I think this, I think that. So there are extremely specific numbers involved, and the big one is p, also called the p-value. If you're going to write it in papers, it should be a lowercase p, and it should usually be in italics. I try to remember to do that in my PowerPoints, but occasionally I forget with the formatting. It's a pretty picky little thing. So one way to make a decision about the null hypothesis based on the observable data is to do this. You work backwards. You ask how probable these results would be if the null hypothesis was true. Now, if you'll notice, this is extremely similar to what we've been saying, and I've been saying this in sort of shorthand, a little more informal, kind of mathematically sloppy language. I've been saying, would these data have happened if the null hypothesis were true? Well, it's not a yes or no thing, even though I've said it that way a few times for simplicity. It's actually a probability thing. How likely would these data have been to happen? How probable would these results have been to happen if the null hypothesis is true? And P is this probability. So think about this. Now that I've explained this, pause the video and think about this. Which of the following is a result that is more in favor of the alternative hypothesis? Assume you've done a study and you calculate your p-value. And let's say you get a p-value of 0.01. Or let's say you get a p-value of 0.99. Now it's a probability, so it can go from 0 to 1. So 0.01 is very small, and 0.99 is very big, as probabilities go. Is this probability, do we want a big probability to be in favor of our alternative hypothesis, or a low probability? And keep in mind that P means the probability of observing the data we observed if the null hypothesis is true. But this question is about which is more in favor of the alternative hypothesis. So think about that for a minute. And then after you're done, unpause it, and we'll talk about the answer, which is this one. We like small p-values. The question is why. So let's work through why. You might know why, and this could be insulting and you can skim ahead, but if not, think through this with me. This is where things start to get tricky, not ridiculously complicated, because we're talking about one probability, but it is a probability from a conditional probability statement, which is a little bit complex. And we're going to start stacking that together with other things and trying to see where it came from. Let's go back to our diagram of the world according to the null hypothesis being false or the null hypothesis being true. So either the null hypothesis is true or false, right? And we're only going to have really two outcomes. We're either going to reject the null hypothesis and retain the alternative, and that can happen up here if the null hypothesis is false, or down here if the null hypothesis is true. That's one decision we could make. The other decision is we retain the null hypothesis and reject the alternative, and that could happen if the null hypothesis is false or if the null hypothesis is true. A p-value is only a probability of one of these things. It's the probability of this one happening right here. So p can't actually happen unless the null hypothesis is true. So p is the probability of this happening, which is a conditional probability. This can't happen if the null hypothesis is false. You can't have a p-value if the null hypothesis is false. Not really. P is the conditional. It's the probability of this happening if the null hypothesis is true. So the p-value has the conditional probability built into it. Okay. So we have to remember very clearly that whether we reject the null hypothesis or retain the null hypothesis, either way could be an error or the correct decision. In both cases, because we don't know whether we're living in the universe of the null hypothesis being true or the universe of the null hypothesis being false. We can have any decision we make could be an error or a correct decision. So the p-value might or might not be a probability that's actually happening. We talk about p-value, but we have to remember that it's conditional. We don't know whether the thing that it talks about the probability of has actually happened, because it's the probability of rejecting the null hypothesis of getting data this extreme if the null hypothesis is true. So let's take one example that I like to talk about for p-values. So a lot of this is going to be examples. Let's say there's somebody, Lenny Lightfingers. Sounds like a crook name, I made it up. So Lenny Lightfingers Lamont is picked up by the cops 20 minutes after a local store is robbed in a smash and grab theft. So Detective Krupke, reference, thinks the alternative hypothesis. He thinks Lenny robbed the store. So this is kind of the legal situation, but it's translated to interrogation. Lenny would prefer that the police believe he did not rob the store. Now we don't know whether he did or not. Detective Krupke would like an external observer, like say a judge or something, to believe that he did rob the store, but Lenny would prefer this external observer to believe he didn't. So we've got a null hypothesis type person and an alternative hypothesis type person. The evidence, let's say it's $25,000 was found in his briefcase, and Lenny is not a wealthy man. And of course he comes up with some explanation, some null hypothesis. Well, that's my wages for the last 4 years, just like the extras I've been saving up in pennies under my mattress. Nobody can verify it because it was under my mattress, right? So he's got his own hypothesis, the null hypothesis, which says nothing is going on here. The alternative hypothesis is yes, something's going on here. He robbed the store. So this situation leads us to a very plausible p-value question. So an interrogator like Sergeant Krupke could say, all right, let's play devil's advocate here. Let's assume you didn't rob the store. If so, if you didn't rob the store, Lenny, how likely would it be that you would be walking along that street 20 minutes after the robbery with $25,000 in your briefcase? So this is very much the kind of question an interrogator might ask. They might say, let's assume that you're telling the truth. Then how likely is it that we would find this evidence, this very condemning evidence? So think about the how likely part, the what is the probability part. What does it mean if the probability is low? Does it mean we're more likely to believe that Detective Krupke's theory that he robbed the store, or that we're going to be more likely to believe Lenny's theory that he didn't? And what does it imply if the probability is high? If the probability is low, you have to kind of do some reversals. It's like a double and triple negative type sentence we're talking about here. If the probability of that p-value question is low, then that's sort of support for Detective Krupke's hypothesis. If he didn't rob the store, then what's the probability that he would have $25,000 in his briefcase? And you could say, 1,000,000 to 1. In general, he never has $25,000 in his briefcase. So if he didn't rob the store, it would be extremely unlikely that that would happen. Low p-value. Or what if Lenny constantly walks home the payroll from his job and he's constantly got lots of money in his briefcase? If he didn't rob the store, what's the probability he would have 25,000 in his briefcase? Well, it's pretty high. He does this every week. This is common. If Lenny's null hypothesis is true, this is something we would expect, and that should make us less likely to believe Detective Krupke's theory. Now, in either case, either theory could be correct, right? It's just the p-value can give us a guideline to lean towards one theory versus the other. So here's a diagram. If you rob the store, yes or no. So he's guilty or he's innocent. If he's guilty, then the alternative hypothesis is true. And then if the data are most consistent with the alternative hypothesis, like that $25,000 is consistent with the idea that he did rob the store, then we'll say he's guilty. If, like, let's say he only has $5,000 or $1,000 or $500, then we might say the evidence is more consistent with him not robbing the store, and we would say he's innocent. But in this situation, he is guilty. And here we made a mistake. Here we said the right thing, but here we made a mistake. It depends on what that evidence is and how we judge it, whether we're going to make the correct decision or a false decision. Now, if he's innocent, we could do the same thing. If the data seems most consistent with the alternative hypothesis that he's guilty, we might say he's guilty. We reject the null hypothesis. That would be a mistake, because in this world down here, the pink world, he's not guilty. The null hypothesis is true. Or the evidence could seem to us more consistent with the null hypothesis, in other words, with Lenny's own story, and then he's innocent. And then we would make a correct decision. So that's how those probabilities map out. And P is the probability of making this mistake. Do you understand that? It's the probability, if the null hypothesis is true, the probability of this data here being so consistent with the alternative hypothesis by whatever criteria we've decided that we reject the null hypothesis. So P is the probability of making this mistake if the null hypothesis is true. But keep in mind, the decision itself could go either way. So all we're going to know is the probability if the null hypothesis is true. We're not going to know if we made the mistake or not. We've always got that uncertainty. So low p-value implies that Lenny might be more guilty. A high p-value seems more consistent with the idea that he's innocent. I think through both of these. Think through why low p implies alternative hypothesis, guilty, and high p implies null hypothesis, innocent. Make sure you can think through these and understand why low p implies this and high p implies the other. P is not necessarily reality. It's based on imperfect data. So we're not proving anything. We're not rejecting any hypothesis in a fundamental way. And P is just the result of a particular method of crunching the numbers. We use probability theory, kind of work backwards and say, if this was true, then what's the probability of this happening? And P is what we use to make a decision about the null hypothesis. So when we crunch the numbers, we're going to end up with a p-value. Now, software will just give you a p-value. Sometimes it doesn't call it a p-value, but you have to learn what it calls it. Usually it just says P. And then you look at that number and you say, is the number low? We reject the null hypothesis. Is it high? We don't reject the null hypothesis. So one final note, we probably don't care about whether Lenny had exactly $25,000. We just care whether he had a lot, right? It's not likely that he should be carrying a lot. So we'll set some value and say anything above 25,000, that's a little bit crazy. So we care about whether he had, if we find him with $20,000, for instance, we might say, what's the likelihood that he would have $20,000 or more? Because we wouldn't say, oh, detective, actually, we found out he's got $21,000 in his briefcase. The detective isn't going to say, oh, well, I was wrong. I mean, my whole theory was based on him having exactly 20,000. No, he'd say 21,000 is still pretty bad. So anything from 20,000 on up is bad. So we care about a range of values, and actually the probabilities work much more nicely with a range of values than a specific value also. So P is the probability of something or more extreme, an entire range going out to, some undefined extreme. It's the probability of that happening. So if the null hypothesis is true, then what is the probability, and probably still from 0 to 1, of observing these results that we got, or more extreme? This is the p-value. So when somebody asks you what p means, the only real answer is this entire conditional thing. P is the probability of observing the results that we observed, or more extreme results. Extreme means more extremely unlikely if the null hypothesis were true. So It's the probability of observing the results we actually observed, or more extremely unlikely if the null hypothesis itself happens to be true, which we don't know. That's that whole conditional statement, that is p-value. And to understand p-value and to make sure you understand hypothesis testing, you've got to get this whole thing. So that's the whole thing, the data being most consistent with the alternative hypothesis, even though the null hypothesis is true, and therefore us rejecting this, making this whole decision. Actually, the p-value is more, this part, the data being more consistent with HA here than the alternative hypothesis. The decision is what we will make based on the p-value. I've been a little sloppy with that. We'll talk about that more. Here's another analogy. I'll go through it a little more quickly. The rest of these slides are mostly just analogies. An anonymous caller buys a whole bunch of nitrogen-based fertilizer and diesel fuel from a farm supply store in the Midwest, and these can be combined, if you're knowledgeable, to make a bomb, sort of like Oklahoma City. That's what that was, a van full of that stuff parked in the basement of the Oklahoma City federal building there. So here's the question. Not very many farmers really buy their fertilizer at that time of the year, but some do. So is this a terrorist planning another Oklahoma City bombing, or is this just a farmer? The null hypothesis is just a farmer. The alternative hypothesis is a terrorist. Null hypothesis, nothing unusual going on here. This is nothing interesting, nothing to see here. Alternative, definitely something going on. So the p-value question, and we often write this way, p is probability of the data given the null hypothesis. That's a shorthand for the probability of observing the data we observed, or more extreme, that's what the data part means, given H0 means that the null hypothesis is true. So p of data given HO, that's a way we pack the whole p-value down into a tiny little bundle, as long as you understand what each of the pieces of the bundle means. The p-value question is, if the null hypothesis is true, so given H naught, if it's just a farmer, then what is the probability, p, that he or she would buy this much fertilizer or diesel or more at this time of year? So that's data. So this is a way of turning that p data given HO into a sentence that makes sense. So the p-value question, if it's just a farmer, if the null hypothesis is true, in other words, what's the probability that he or she would do this? So now you should be able to think a little more clearly. What does a low p-value imply? And what does a high p-value imply? Which one would make you think a little bit more that it's a farmer, and which one would make you think a little bit more that it's a terrorist? So the probability diagram I've got here, is the buyer building a bomb? Are they a terrorist? Yes or no? If they are a terrorist, then we still might find the data a little more consistent with the idea that they're a terrorist or that they're not. And if they're not a terrorist, we might find this data, that the fact that they bought all this stuff, more consistent with the idea that them being a terrorist or not. And the p-value is the probability of us finally doing this, of this outcome. So a couple more quick examples. You can, if you feel like you've really got this locked in, you can move on from this video if you like, but we've got a couple more examples because historically people have a hard time with this. So your friend Bob says he can predict the future. He correctly guesses 5 of 6 coin tosses. You know, he's saying heads, it is heads, tails, it is tails, tails again, it is tails, right? He's only wrong once out of 6 times. The alternative hypothesis, he can predict the future. The null hypothesis, no, he can't. Nothing going on here, nothing interesting. So what would we expect if he cannot predict the future? So this is the p-value question. Would we expect 0? And this is an interesting question because no, we wouldn't expect 0. If he's guessing randomly, he should be right half the time. As they say, a stop clock is right twice a day. I mean, this applies in a lot of situations. If you're guessing random coin tosses, you wouldn't expect 0 if you are just guessing randomly. We'd expect on average over many, many tries for you to guess half. But he might not guess half right now. I mean, he might be a little above half or a little below half. Half is just what we would expect on average. Maybe he just got really lucky. So the p-value question is, if he's just randomly guessing and therefore just really lucky, what's the probability that he would guess 5 or 6 coin tosses correctly in 6 tries? So how would we calculate this p-value? This is how we would write that out. The probability of data given H naught is the probability of 5 or 6. So it's not just the probability of him guessing 5 things, it's 5 or more extremely unlikely, right? So more extreme. So 5 or 6, he could have guessed 6 out of 6. That's the only other more extreme thing What's the probability of him guessing 5 or 6 correctly in 6 tries, given that he's only random guessing? And actually, probability theory can answer that for us pretty specifically. That's something that we can work out without too much trouble. So here's another possibility. Is a student cheating or not? A high school teacher suspects that students are stealing answers from his office before the exam. So he makes a quiz that's totally crazy. The answers make no sense. But he stores the key in his office. And Agatha, the star student, gets all 10 questions right according to the key, even though they're crazy questions. So did she cheat? The alternative hypothesis is that she cheated. On the null hypothesis, she didn't cheat. She just got very lucky. There was no way to guess correctly, and she just got lucky in guessing. So what would we expect if she did not cheat? And that's an important question that helps us define what the null hypothesis is. It's not that she would get 0. In this case, we would expect that she would get the expected average number of random correct guesses. Our best guess, if there are 5 options for each question, 20% is 1/5 of 100%. So 1 in 5 chance, we would expect, since there's a 1 in 5 chance on each question, then across 10 questions, on average, she would be getting 1 in 5. So she would get 20% of those 10 questions correct. If she were just guessing, we would estimate that she should get about 2 questions correct, but she got 10. But of course, maybe she just got lucky. That's the way random works. On average, over many tries, she should get 20% of the questions right, but maybe she actually got them. So how do we calculate the p-value? The probability of the data given the null hypothesis, we could put it in this way. The probability of getting 10 questions right, there's nothing more extreme. I made this example an easier one. So there's nothing more extreme than 10. There were only 10 questions. What's the probability of her getting 10 questions right if she was just random guessing? And that would be the end of this lecture.